So now we're going to talk about the TCA cycle, the tricarboxylic acid cycle, Krebs cycle. These are all the same name, right? So before we learned about how glycolysis creates sugar, right? So sugar from that is being broken down to pyruvate. Pyruvate is carried into the mitochondria where it's converted into acetyl-CoA. And now acetyl-CoA enters this new cycle called the Krebs cycle or TCA cycle. It's the same thing, right? So the best way, if you look at this nice little schematic I put, you're probably overwhelmed, like what is going on? I am lost completely, right? So the best way first to understand this entire cycle is through this little acronym I made, okay? So you can either use an A or an O in the beginning, right? And you can just call it SCS-FM, right? And this is telling you the order of all the metabolites in the Krebs cycle, right? So we begin here at the top. You have acetyl-CoA and you have OOA, so oxaloacetate. They combine to form citrate with the help of this first enzyme called citrate synthase, right? So if you notice about this entire cycle, all the cycles here are irreversible. So whenever this gets converted, this happens. There's no irreversible step that we've learned, for example, in glycolysis, where you see some reactions to be reversible where others are not, right? So these are all irreversible, where you see a hydrolysis reaction coming in, and you have these two chemicals combined, the OOA and acetyl-CoA, combined to form citrase with the release of this CoA thiolate, okay? Now, citrate gets converted into isocitrate, right, with this chemical called, this enzyme called aconitase. Aconitase is sort of like another form of an isomerase. So the chemical molecular formula is the same, however, the actual bonding changes, right? So now you go from citrate to isocitrate. So we go to C to I, right? Now, when we look at the conversion of isocitrate to alpha-ketoglutarate, I to A, there's several things that takes place, right? So you see first that there's a lack of carbon dioxide. So there's a decarboxylic reaction that takes place, right, with this enzyme isocitrase dehydrogenase. And if you remember, when we hear the word dehydrogenase, usually a lot of these enzymes in these different metabolic pathways are involved with the NAD plus and NADH complex, right, here. So you see that there is a oxidation process coming. So isocitrate becomes oxidized, right? So it loses a hydrogen group and it becomes alpha-ketoglutarate. That's A. So A to S, now, if we look at this diagram here, alpha-ketoglutarate gets converted into succinyl-CoA, right? The enzyme involved is the alpha-ketoglutarate dehydrogenase, right? And this is where you have the CoA thiol group coming in and bonding with this alpha-ketoglutarate in order to give this CoA subgroup in this molecule, right? But what else happens is you see another decarboxylation reaction that takes place. And finally, if you look at the name again, dehydrogenase, when you hear the word dehydrogenase, there's probably an NAD plus exchange. So there's oxidation reaction that's taking place at the same time where the NADH is created in order to create this final product of succinyl-CoA, right? S to S, succinyl-CoA becomes succinate, right? And this is where we have an instance of GTP production, right? So ATP, you remember, it's adenine triphosphate. GTP is guanine triphosphate, right? So it's same energetic phenomena as the ATP, right? However, they're using just a different type of nucleotide, right? The enzyme involved is the succinate thiokinase, right? So you have a kinase where there's a phosphorylation that takes place. There's a dephosphorylation here, right? So you lose the phosphate. And then you have this thiol group here, so this CoASH, right? So you have this thiol sulfur group that is being released out to create succinate. S to F, you have succinate being converted into fumarate. Fumarate, again, uses this enzyme, succinate dehydrogenase. Now we have this new form of oxidizing agent. So this oxidizing agent, FAD, gets converted into FADH2, removing 2 of the hydrogens from the succinate in order to give you fumarate. All right. F to M, you have fumarate getting converted into malate. So fumarate uses this enzyme that breaks down fumarate, called fumarase, with the water, right? So this is sort of a hydrolysis reaction taking place. And then you are left in the end with malate. So malate now, so as we come to the final letter of this acronym that I posted for you, malate now needs to restart this entire cycle. So it converts the malate now back into oxaloacetate through a dehydrogenation, right? So malate dehydrogenation takes place here. And so you again have the NAD plus coming in and removing the hydrogen in order to have NADH and H remaining. So you have this oxidation that takes place of the malate in order to have this oxaloacetate, right? And this is a continuous cycle that takes place, right? So in the end, when you have the final product, you have 1, 2, 3 NADHs that are created. You have 1 GTP and you have 1 FADH. These are all the enzymes that are being created. So 1 FADH2. So now why are these relevant? Why do we care about these things, right? So what becomes important about these molecules is in the molecule is the mitochondria, electron transport chain, where we have instances of oxidative phosphorylation. So all of the NADHs, the FADH2s, and all of these migrate into the electron transport chain, and they allow for the actual reduction of certain molecules that allow for the production of excessive ATP. And so this is basically the general schematic of the Krebs cycle or TCA cycle, or the citric acid cycle. There's so many names for these things. Just pick one, whichever one's your favorite that sounds the best, and you can use that as an example.